All right, good morning, chemists. We'll get started now. So we're going to jump into chapter 16 and talk about acid-base equilibria. This is chemical equilibria that's happening in water. So everything is typically aqueous. In chapter 15, we talked about general chemical equilibria, but we looked at gas phase things, aqueous things. So we'll specifically go into the nitty-gritty details of different types of big Ks. The next two chapters, we're going to be exploring a lot of different big K values, but in general, understand that big K is products over reactants. And so when given a chemical equilibria, we still follow those same rules that we used in chapter 15. But this is specifically for acids and bases. Okay, so just some announcements before moving on. I just published the midterm 2 preparations page like 10 minutes ago. So that page contains the supplemental information you'll get at the exam, information about the coverage and the makeup policy. My 2 paper practice midterms are posted. The department has not posted theirs yet, but it'll make it to that page once they do. And then finally, my Zoom review session that's also in this room will be next Tuesday because our exam is next Friday. This Friday is just a regular recitation activity day. So that Zoom session is next week for our midterm that following Friday. And it's, Tuesday, but it has to start at 5:30 this time. Instead of 6, it's at 5:30 until 7 because there's an exam happening in this room at that same time. Right, so, okay, so that's the outlook for the next 2 weeks. Okay, so let's talk about acid-base equilibria. But before we get started, because what we're going to learn here is go into detail about more weak acids, weak bases, strong acids, strong bases. We covered that a little bit in Chemistry 1210, so why don't we just remind ourselves what those 7 strong acids are from Chem 1210. Go. Someone name one. What? ClO4, just ClO4? There has to be an H, yeah, so you got the ending part, yeah, so all of these acids do have an H plus present in it somewhere, all right, so HCl4. Another one is HClO3, so chloric acid and perchloric acid are both strong acids. Then we also have H2SO4, okay, and then one more of the polyatomics, of the polyatomic types, the ones with the long names. HNO3, yep, that's another one, yep, HNO3, nitric acid. So those are the 4 polyatomic strong acids, and then there are some binary acids that are also strong. You can use the periodic table to help you. Which ones? HF is not a strong acid, but you're right in looking at the halogens. So the strong acids that are binary are just HCl, HBr, and HI. So basically all of the halogens except fluorine. Fluorine is the weird one because it's so small and electronegative. Right, so HF is a weak acid. And so what helps us here is as long as you know the 7 strong acids, any other acid that you encounter is a weak acid. Do you remember how we recognize strong bases? Strong bases, what makes a base a base? It has hydroxide present in it, and so most ionic compounds that have a hydroxide in it are strong bases. Do you remember the one weak base we had you memorize in 1210? The one was ammonia. Ammonia was the one weak base that we talked about in 1210, but in this chapter in 1220, we're going to learn a lot more weak bases, so we're going to expand on that. Okay, all right, so that just kind of gets us started here since we're going to be talking about acid-base equilibria. Got a cool demo and something I'm going to try out, and I don't know what the outcome is going to be. All right, yes, I have a monster up here. I'm going to get blasted today because I have two classes, so I have 2 monsters with me. I guess I don't have to drink it, but I should. I bought it. Okay, all right, so let's get started. All right, so acid-base equilibria, just to reference you, only the first half of this chapter is on midterm 2, and then midterm 3 is the second half. So all the pH calculations and strong acids, strong bases are in midterm 2, while the weak acids, weak bases at the second half of the chapter is midterm 3. So it's about separated around slide 25. So the first half, midterm 2. Second half, midterm 3. All right, so we're going to expand on this idea of neutralization reactions as well. You did this in Chem 1210. You reacted acids with bases to give water and a salt. We'll expand on that. HCl and sodium hydroxide, those are both strong acids and bases. So we're going to extend that to also what happens when you neutralize weak acids and bases. So understanding whether you're in the strong realm or the weak realm will help us here. Basically, first half of the chapter, just strong stuff. Second half of the chapter, weak stuff. And because this chapter is separated by 2 midterms, the homework is also separated by 2 homework sets. So I do anticipate that the first set will be due on Monday, but the second set won't be due until after midterm 2, because I'm not evil. Okay, so acids and bases. So how scientists determined what were acids, what were bases, were primarily off of observations. So, you know, I love this part of the chapters 16, 17, because they're very applicable to life. We work with acids and bases all the time. All right. We enjoy drinking acidic things. You might not think of it as acidic, but you can definitely tell. It might not be like overly acidic, so acidic like it's dangerous, like the HCl that you work in lab. But yes, the things that we encounter on an everyday life are usually acidic or basic. And so back in history, when scientists were trying to determine what were acids, what were bases, historically they actually tasted these things, which you shouldn't do in lab. But typically scientists categorized acids as things that tasted sour, kind of like lemon juice. Even sodas have that sour taste that we typically enjoy. Versus bases, if they tried a chemical and it was bitter, they categorize that as a base. And so of course we don't do that today, but we'll explore some other categories of ways to categorize acids and bases by looking at it at a particle level, but we'll expand on this a little bit later. This is on midterm 2. But I want to just get into pH calculations first, and then we'll come back to these ideas, the different categories of acids and bases. All right, so don't taste these things. Don't taste them. Okay, so we're going to go out of order a little bit. We're just going to start with pH calculations. How can we numerically categorize something as an acid or base? Most of the time, most people reference themselves to the number 7. All right, a pH of 7, typically we associate with what kind of solution or what kind of material? If it's pH 7, it's pH neutral. Yeah, but there's a small caveat there that I will explain in a little bit. So let's learn about calculating pH concentrations. All right, so when we have solutions, even just pure water, there's always a little bit of H plus and OH minus present in that water, even pure water, and we'll talk about that in a little bit. So these concentrations are very, very, very small, all right? They're very, very, very small. H plus and hydroxide in solutions, very small, usually like 10 to the negative, 6 molarity, all right? I don't know about you, but it's very annoying to constantly write scientific notation. Do you enjoy writing scientific notation? No. Do you enjoy looking at really, really, really small numbers? No, they're not fun to look at. So that's what the pH scale is for, to help us visualize how big or how small these numbers are in better looking numbers. So in essence, P is a function. P means negative log. All right, you take a number and you take the negative log of it, and now you have the P value of it. So pH means you take the negative log of the H plus concentration of your solution. We can also look at the hydroxide concentration. We can take the pOH and understand the pOH of the solution by taking the negative log of the hydroxide concentration, right? So see how the name, like pOH, we take the concentration, we take the negative log of it to get pH. So if I asked you what is the equation for P bananas, all right, that's just a function. It just means negative log of the concentration of bananas, all right? So P just means negative log of something, right? And so you see those two equations here, pOH, negative log, hydroxide concentration, pH is negative log of your H plus concentration. And what's special at 25 degrees Celsius and 25 degrees Celsius only is that these two numbers, pH and pOH, add up to 14. All right, and so that's why we see, a pH of 7 gives us a neutral solution because the concentrations of H plus and OH minus are equal at that pH. So we'll come back to this idea in a little bit. So let's do some calculations. Let's convert H plus concentration to pH. All right, so I give you a concentration here. See, it's a really small number. That's annoying to write out, right? Like on a stock bottle or something. So it might be better to just represent that bottle or that solution given its pH instead. So the pH of this solution, if it's 1.5 times 10 to the negative 5, is negative log 1.5 times 10 to the negative 5. And that's simply it. And so if you stick that into your calculator, you get a value like 4.82. All right, so what kind of number do you want to be looking at? The really, really small number or 4.82? 4.82 looks better to our eyes. All right, and so let me spend a second and talk about sig figs for logarithms. So we've never done this before, so I'm going to introduce it now. So when we do multiplication and division, it's simply you look at the values, you pick the number with the smallest number of sig figs, and that's the one you take, right, for your answer. With logarithms, it's a little bit different, all right? When we take a log of a number, so log of 1.5 times 10 to the negative 5, how many sig figs does that molarity have? 2, yes. So we need our answer to have 2 significant figures as well, but there's a special rule with logarithms that the whole numbers that are in front of the decimal point, right, this value does not contain any sig figs. Right? This 4 is telling us the magnitude of the number. It's telling us how many place values I need to move my decimal place. So all the significant figure information actually comes after the decimal point. So the rule is squared down here, all right? So for logarithms, the sig fig rule is that the number of sig figs in your molarity is the number of decimal places in your pH value, all right? So we see that H plus has 2 sig figs, so our pH value has 2 decimal places. So it looks like the value has 3 sig figs, but remember that 4 is just telling us the magnitude of this number. All right, so we got our pH. How should we get our pOH then? If you look at all of these boxed equations, the one that we probably want to use is pH plus pOH equals 14, all right? So since we have our pH value, we can just simply subtract it from 14. So 14 minus 4.82, we get something like 9.18 would be our pOH value there. And so both those numbers do add up to 14. We're assuming this solution is at 25 degrees Celsius. 95% of the work we'll do in this course is happening at 25 degrees Celsius. All right, so that is working from concentrations to pH. So now let's do it the opposite way. Let's go from pH to molarities of our solution. So we have a solution that is pH 11.51. Is this solution basic or acidic or neutral? What do you think? So let's look down here. Let's look down here. All right, so a solution is always neutral when H plus concentration equals hydroxide concentration. So a pH of 7 is neutral. pHs lower than 7 are acidic. pHs higher than 7 are basic. So let's just actually get the concentrations and I'll prove it to you that this solution is actually basic. All right, and so I'll show you. All right, so to undo a pH value, we have to undo a logarithm, and so these logarithms are base 10. So our H plus concentration is simply 10 to the negative pH value that's given. So this concentration will be 10 to the negative 11.51. So that's how we undo a logarithm. Right? And so if you stick that into your calculator, you get a really small number. How many sig figs should my number have? 3 point, should I keep going? It should have 2 sig figs, so 3.1 times 10 to the negative 12 molarity H plus. Yes, 2 sig figs because my pH value has 2 decimal places. All right, so we're kind of using this rule but in reverse. All right, so 3.1 times 10 to the negative 12 molarity is our H plus concentration. So let's just continue this and get our hydroxide concentration, and this will help us determine whether this solution is acidic or basic. So to get the hydroxide concentration, we simply do negative 10 to the negative POH, but I didn't give you the POH. So how do I get the POH of this solution? Subtract from 14. Yeah, so this pH value implies that the POH value is 14 minus 11.51. So that means our POH value is something like, what is it? 2.49. All right, and so then we get our H plus concentration is 10 to the negative 2.49. And so stick that into your calculator and you get something like 3.2 times 10 to the negative 3 OH minus concentration. So in this solution with a pH of 11.51, both of these concentrations are present. So tell me, given the answers we just got, H plus and hydroxide, which substance is more present? Which one has the higher concentration, hydroxide or H plus? H plus? Now, so look at the exponent on the 10 to the, all right, so to the negative 12 means we have to move the decimal place 12 times, so that's a really small number, versus to the negative 3 hydroxide, we only move the decimal place over 3 times, so our hydroxide concentration is much, much greater than our H plus concentration because the OH minus value is a lot larger. And so now, can you tell me, is this solution basic or acidic? It is definitely basic because there's a lot more hydroxide present. And that's basically our rules for whether we have an acidic solution or a basic solution. That it's acidic when H plus is more present in concentration, basic if hydroxide is present in a higher concentration. All right, and so only at 25 degrees Celsius is a pH of 7 an example where hydroxide and H plus are equal to one another. Those two concentrations are equal to one another. So we have a neutral solution when both of those two things are equal to one another. All right, so those are our calculations. So let me introduce the idea of where this H plus and hydroxide comes from. And it comes from water. All right, so I've been lying to you for the past semester and a half, where I said, oh, water is this pure substance, okay? It's this molecule that doesn't break apart. If it breaks apart, that's a chemical change. So I've been lying to you all this time. H plus is actually a substance that undergoes an equilibrium, right? Pure water. Right? When we think about a pure water sample, we think of H2O particles copy and pasted a billion times, but that's actually not what it looks like. Water actually is what we call, it undergoes autoionization, meaning even in its pure form, it separates, it undergoes this equilibrium, and this is what happens to water. Right, if we have a pure sample of water, you just think of, you know, like 2 water molecules. What happens is that one of the H pluses on one of the waters combines with another water molecule. And so what you see here, this is what we call autoionization, is where we make a H3O plus. We call this hydronium ion and a hydroxide ion as well. All right, so this equilibrium happens even in a pure sample of water. So this particle diagram kind of does a better representation of it. So here's one neutral water molecule. Here's another neutral water molecule. Basically, one of these hydrogens is going to hop on the other water molecule. So then you see that one of these water molecules has 3 H pluses, so H3O plus, while the one that gave up that H plus is now just hydroxide. All right, so this happens in water, but just a tiny bit. This process, the autoionization of water, has its own K value, Kw. We call it Kw because it's for water. All right, so it's a specific K value specific for water and this process that water ionizes itself to H plus and OH minus. All right, so we can write the K expression for this if we look at this chemical equation, the equilibrium. All right, we can write the K expression just like in chapter 15 where we do products over reactants. So you see that we put an H plus concentration, an OH minus concentration, but do we put water into our K expression at all? No, why don't we include it? It's a liquid, yeah, so only these two things that are aqueous, that are dissolved, go into our K expression, just like before. So the Kc value for this process is H3O plus times OH minus concentration, but specifically we call this Kc value Kw, all right? So the H3O plus is the acid portion of water, and the OH minus is the base portion of water. All right, so we can also associate acids to exist as H3O plus or hydronium. But see, chemists are lazy, and oftentimes we don't like to write the full hydronium ion out. That's actually what acids exist as in water. H plus doesn't exist in water, just a free H plus proton floating around. It's always attached to a water molecule. But that's just a small detail. Chemists are oftentimes lazy and will write it this way, where Kw equals H plus times OH minus concentration, just because it saves us a couple of letters to write. But in this case, you can just think of H plus is basically the same thing as H3O plus hydronium. They're basically the same thing, all right? Just know that H plus doesn't exist. It's always actually attached to a water. Okay, so let's calculate the concentrations of H plus and hydroxide using our Kw value that's given. So this is kind of just chapter 15 review, but we're using the same skills, but we're applying it to acids and bases. So let's calculate the acid-base concentrations and the pH of pure water at 25 degrees Celsius, and I'm telling you that the Kw for this reaction is a very small number, 1 times 10 to the negative 14. This is no different than chapter 15, okay? So if we have pure water present, we're gonna be doing an ice table, all right? Let's put pure water into our sample. So I'm just gonna put a random amount. I'm just gonna say an N amount, and I have 0 of this stuff. All right, I'm just going to throw a bunch in a beaker. Tell me, which way does this reaction have to go? Forward, forward. So what should my change line look like? Underwater, it should be what? Minus 2x, yep. And then under the two products, it should be plus x and plus x. Does this look any different than chapter 15? No, it doesn't. So then you add up all of those columns and you get that at equilibrium, there's going to be an n minus 2x amount of water, an x amount of hydronium, and an x amount of hydroxide. All right. What's the trick with ice tables at this step? Once we've kind of completed our ice table, the E line goes into the K expression. Yeah, so the K expression, which is given as Kw, is equal to the hydronium concentration times the hydroxide concentration. And so I'm just going to shove those E line values into that. So Kw is equal to x squared. So note how I started with, like some of you might feel anxious that I just put a random amount of water into this container. So here I technically have two variables present, n minus 2x, but do I ever put that n minus 2x into the k expression? No, so it actually doesn't matter what value. I could have made up a number, I could have put 5, and again, it doesn't matter because we don't put liquids into our k expression. So kW is equal to x squared, and that is equal to 1 times 10 to the negative 14. All right, can we solve x without the quadratic? Yes, we can. We can simply just take the square root of both sides, and so we see that x is equal to 1.0 times 10 to the negative 7 molarity. All right? But as chemists, we need to apply and understand what that x represents. Yes, it's the concentration, but the concentration of what? It's the concentration of, look at your ice table, what is x? It is the concentration of your H plus at equilibrium and, or sorry, I'll write hydronium. I won't be lazy yet. H3O plus concentration, and it's the concentration of your hydroxide. Both of those things are equal to x, all right? So now we have our H plus concentration, we have our OH minus concentration. You can then go ahead and calculate the pH by taking the negative log of both of these things. And so we see 1 times 10 to the negative 7, that is an exact pH of 7. And so, can you tell me, is this solution neutral? Yes, it is, because H plus equals OH minus concentration. So this solution is, in fact, neutral. Right? It's pure water. We didn't put anything in it. It's pure water, so we should understand that to be neutral. All right, so that's how we calculate the pH of pure water using that kW value. So the reason that a neutral solution at 25 degrees Celsius is a pH of 7 is because of that value of kW at 25 degrees Celsius. Okay, all right, so, let me ask you this. Okay, if I tell you that this autoionization is, let me go down here. If I tell you that this autoionization process is endothermic, if I heat this reaction away from 25 degrees Celsius, will the value of K change? KW, will it change? Yes, it will, because adding heat pushes the reaction towards what side? The product side. And so if adding heat shifts the reaction to the product side, how do you think the value of K will change? It'll get bigger, and that's exactly what happens. So this is why Ks are temperature dependent. KW is temperature dependent. That's why I keep saying at 25 degrees, because when the solution is not at 25 degrees, the value of kW changes. So at 50 degrees Celsius, so we heat up the solution a lot, kW is actually 5.5 times 10 to the negative 14. So that's consistent with us thinking, oh, heat this reaction up, pushes to products, K gets bigger. All right, so let's do the same exact thing and calculate what is the concentration of everything and the pH of pure water at 50 degrees Celsius with this new kW expression. So we're going to do this the exact same. We're just going to use a different K value. So let's throw a random amount of water in. How much water do you want to put in initially? Anyone? A random number? 10? Sure, we'll just put 10. It doesn't matter, okay? Just some n value, and we have 0 amounts of everything else, right? So this equilibrium has to shift to what side? It has to move forward, yeah. So under water, we're going to lose 2x. We're going to gain x amount of hydronium, x amount of hydroxide. So at equilibrium, we'll have 10 minus 2x of H2O. Again, it doesn't matter how much we put in because that's not going to go into the equilibrium expression anyway. But what is important is that we have an X amount of hydroxide and hydronium. Again, this is the exact same as chapter 15. Right? And so what do we do now? Put it into the K expression. Put that E line into the K expression. So KW is equal to X squared but no longer is it equal to 1 times 10 to the negative 14. At 50 degrees, this is equal to 5.5 times 10 to the negative 14. All right, so we do it the exact same. To calculate x, we just take the square root of both sides, and so that we see that x is equal to 2.3, okay, this should have 2 sig figs, but I'm going to just keep a couple extras, to 10 to the negative 7 molarity. So this concentration is the concentration of what? In the ice table, x is equal to H plus concentration or hydronium concentration and hydroxide concentration. All right, so how do we calculate the pH of this? Just take the negative log of that number we just got because that is the concentration of H plus. So our pH is equal to negative log 2.345 times 10 to the negative 7 molarity. And so we get that the pH is equal to 6.63. Is this solution acidic? Does this mean the solution is acidic? No. This solution is what? Acidic, basic, or neutral? It is neutral. This is pure water. So don't think in your head that 7 always means neutral. It does not. We just determined that H plus concentration is equal to hydroxide concentration. Both of them are equal to X. So this is the definition of what a neutral solution is. And so this 6.63 value we just calculated just tells us how much H plus is there, but it also is the same concentration of hydroxide as well. So this water is in fact still neutral. So that's kind of interesting. This is a common misconception that sometimes students have. Oh, if I heat up water, the pH changes, it goes down, so it becomes acidic. But that's not true. We haven't added anything to the water at all. H plus is still equal to hydroxide. The reason your pH is changing is because your value of Kw is changing. All right, so do recall the rules for acidic, basic, and neutral. It's all about comparing H plus to hydroxide concentration, right? But I'll point out that 95% of the time we are working at 25 degrees Celsius, so our rules of pH plus POH equals 14 will be valid, but just not in this case where we're not at 25 degrees Celsius, we're at 50. So we have to use a different Kw value. All right, so that is Kw, autoionization of water, where those very, very small concentrations of H plus and hydroxide come from. All right, this is what I call the magic square, all right? And this is how we relate pH, POH, H plus, and hydroxide all to one another. Do remember H plus also is H3O plus. I'm just lazy and write it H plus, right? These are how we interconvert between all of these. Memorize this. I call it the magic square. All right? How do we turn H plus into POH? What do we do? P means negative log. So negative log of H plus concentration gives us pH. How do we go from hydroxide to POH? We also, the same thing, negative log, but you want to take the hydroxide concentration. That's how we get our POH. All right. At 25 degrees Celsius, so Kw is the 1 times 10 to the negative 14, how are pH and POH related? How are these two things related at 25 degrees? They add up to 14. The question is, why 14? Why 14? It's because pKw, if we take the negative log of 1 times 10 to the negative 14, we get 14. That's why. That's why. All right. So yes, pH and POH add up to 14, but again, only at 25 degrees Celsius. Right. So that's how we relate those two things. To relate H plus and hydroxide for one solution, we use Kw. Understand that Kw equals H plus concentration times hydroxide concentration at equilibrium. And if we're working at 25 degrees Celsius, we know the value of Kw to be 1 times 10 to the negative 14. All right, and then just for completeness, if we wanted to go in reverse, if we were given pH and want to calculate H plus concentration, to undo a pH value, we take 10 to the negative pH. Same thing for POH. If we know the POH, we just take 10 to the negative POH to go back to molarity. And this is your magic square. It's magic because if you know one corner of this square, you know everything. If I give you pH of a solution, you can calculate POH. You can calculate hydroxide concentration of that same solution. You can calculate H plus concentration of that same solution. All of these things are interconnected via KW, all right? So if you know one corner of this square, you know everything. And that's why it's magic, I guess, all right? So do memorize this because on the preparations page, I just posted the supplemental information, and we do not give you any of these values or any of these equations, except we do give you KW at 25 degrees Celsius, right? But we don't give you the equations for KW. We don't give you negative log calculations. So do memorize this, but I anticipate you will just memorize it because we'll be doing these calculations a lot. Okay, so let's do a demo. Let's do the demo. I forgot my goggles. I don't know if I need it. Should I put it on my camera? Nah. Okay, so no one on Zoom gets to, or no one on YouTube gets to see it. Okay, so let's investigate acids and bases and then see what happens to these drinks. Okay, so I have a bunch of beakers here with indicator in them. You've used indicators before, right? What happened with phenolphthalein? What happens with phenolphthalein when you did those titrations? It turned pink. It turned pink in what kind of conditions? When it was acidic or when it was basic? When it was basic, yes. So it turned pink. So this is a different type of indicator that has a bigger range of colors. And on the demo sheet, it says, kids love this demo, because we see a lot of colors. So right now, this is just a bunch of pure water. So let's assume we're at 25 degrees Celsius. What's the pH right now of these solutions? 7. Yes, it's neutral, pH 7. So this indicator is green when it is pH 7. So let's put a little bit of HCl, hydrochloric acid, into one of these beakers. So if I add acid, how should the pH change? The solution should become acidic. Yeah, I'm adding acid, so the pH should go down. So let's see what happens when I add a little bit of acid to one of these beakers. Okay, give it a mix. Okay, so that's what color it looks when it becomes acidic. Yes, kids love this. Do you see why kids love this demo? All right, so that's the acidic solution. It's a like neon orange, all right? Okay, so I have sodium hydroxide here. Sodium hydroxide is a what? Base. So if I add sodium hydroxide to this water, the solution should become basic. Yes, it should. So let's see what happens. Let's see what happens. All right, so that's the color the indicator looks when it's in basic conditions. Okay, so there's acid, there's base. I want to keep them here for your reference, all right? So these green ones are the pH neutral solutions. Here is acidic, here is basic. All right, so I want to introduce the idea of weak acids and weak bases, all right? So let me just talk about this for a second. So as humans, as mammals, we breathe in oxygen and we exhale what? CO2, yes. So CO2 is an interesting substance, all right? So when CO2 mixes with water, H2O, liquid, we get a compound, H2CO3, aqueous. What is that? Can you name that? CO3 2- is what ion? Carbonate, or like calcium carbonate, sodium carbonate. So H2CO3 is called what? Carbonic acid. So if I add carbonic acid to water, the solution should become what? Acidic. So let's check it out. So I'm going to add CO2 to one of these beakers via this scientific instrument, a straw, and we'll see what happens. So right now, this green beaker is pH what? 7, it's neutral, but when I breathe into it and expel my CO2, I'm going to make carbonic acid, and so predict what's going to happen. Okay, I need to like cover it a little bit. Did that change its pH? Yes, it did. All right, so just the CO2 from my breath added enough carbonic acid to make this a different color. All right, so what other tasty things have CO2 in them? Soda. Remember we talked about this in solubility of gases? So here I have my lovely LaCroix, okay, my LaCroix. It's carbonated, so that means it contains what in it? CO2, and we just learned CO2 is a what? It turns into carbonic acid, which is a weak acid. Earlier in the semester, we talked about nitrogen-containing beer, like Guinness. That tastes smoother because there's no there's no CO2 in it. It's actually nitrogen gas-based. And so I figured it wouldn't be very appropriate for me to bring in Guinness. So I went to 2 different gas stations to find a nitro monster. All right, so this energy drink is nitrogenated instead of carbonated. I have no idea what's going to happen. I've never had one of these, so we're going to find out what happens. Because my idea is, okay, this is going to turn the water acidic, right? If I add a little bit of LaCroix, it's going to turn it acidic. But I don't know about this one, right? Because it's nitrogen instead of CO2. I don't know, so let's see what happens. I'm going to make it really scientific, and I'm going to measure same amounts of both of them. And like I said, I'm going to get blasted today because I have to do this twice, and I have two of them. So I'm going to measure this out really good. Okay, that's like 15 milliliters. Okay. Yeah, okay, that's like 15 milliliters. All right, so I have LaCroix, Monster. All right, so let's see what happens. Okay, I'm going to move you over here. This one's going to go here. All right, so what's going to happen to the LaCroix? What should happen to this beaker? It should turn orange. Let's see. Did that turn orange? Heck yeah, it did. So I'm going to mix that up. Real orange, that's real acidic, more acidic than my breath. All right, so let's see what happens to this nitro monster. I'm really excited about this. Okay, let's see. Oh, it also turned orange. I figured this would happen. It would also turn orange, but you might be thinking, but Dr. N, you just said it's nitrogen containing. Shouldn't be acidic, but here's the thing. Humans, we like acidic things. We like to eat acidic things. Rarely do we eat things that are basic. And if I read to you the ingredients on this monster, all right, it's nitrogenated water, sugar, and like the 4th ingredient is citric acid. All right, so why is that acidic? It's not from the absence of CO2, but it's because of the citric acid that's present in this to make it acidic and more tasty tasting. So yes, I figured that would happen. It would still turn acidic, not because of the nitrogen, but because of the citric acid that's in here. So should I try it? I've never had one. Actually, the guy at the gas station was like, "You like those?" And I'm like, "I have no idea. It's for an experiment." So. Oh yeah, that's still tart. Yeah, it's smoother. It tastes like it's flat already. It tastes flat. Ugh, ugh, gross. Okay, I need to wash it down with some coffee. Okay, so there are the demos. Okay, so let's talk about identifying strong and weak acids, but remember, we're going to focus on strong acids for midterm 2, but we will move on to weak acids for midterm 3, but we'll continue on with this chapter 2. Okay, so for strong acids and bases, in order to approach pH calculations, we have to recognize, am I working with a strong acid or strong base, or am I working with a weak acid or weak base? And that will dictate how we approach the pH calculations. So we're going to start with strong acids and strong bases first because they're the easiest. Let's remember that strong acids and strong bases are strong electrolytes. So they ionize fully in water. And this is going to help us with our pH calculation, right? So if I put HCl into solution, or if I tell you that you have a solution and it is, let's say, 1 molarity HCl. If HCl fully ionizes, all right, fully becomes H plus and HCl minus, how much H plus is present in this solution if it fully ionizes? Shouldn't it be also 1 molarity, right? Because it fully ionizes. And this is why strong acid, strong base calculations are much simpler, right? Because we're making the assumption that all of the acid or all of the base is coming from the analyte in question. So it's coming from HCl, coming from the strong acid or strong base, all right? Because these fully ionize. And so note how the arrow that I use here has that full arrow instead of an equilibrium arrow. This reaction kind of goes to completion. Versus, let's look at strong bases. So examples of strong bases, sodium hydroxide, calcium hydroxide. See how the hydroxides fully ionize? I use the fully forward kind of arrow, right? So the same idea here is if I dissolve a strong base in solutions, let's say that my sodium hydroxide concentration, like you calculate it with your molar mass and stuff, let's say it's 2 molarity. If I have a solution that's 2 molarity sodium hydroxide, how much hydroxide ion do I have present in that solution? 2 molarity, yeah, because it fully ionizes, yep. But what if I have calcium hydroxide, and let's say it's 0.5 molarity. If I have a half molarity calcium hydroxide solution, how much hydroxide do I have? So look carefully at the chemical formula. It is 1 molarity, yes, let's have confidence in ourselves. All right, why is it 1 molarity here? Because calcium hydroxide has two hydroxides that it can donate. So just be aware of that given the chemical formula, if there's more than 1 hydroxide that can be donated, and this is specific for strong bases. Right? And so us understanding that strong acids and bases fully ionize will help us calculate those pH calculations. So the next section, we'll talk about weak acids, weak bases. So note what kind of arrow we are using here. Are they the full forward arrow? No. They're the equilibrium arrow. So that means if this is a chemical equilibrium, the reaction doesn't fully go to completion, so we actually have to use K values instead for weak acids, weak bases. So they're a little bit more complicated. We have to use a K value, so that means we probably have to use what? An ice table to calculate the pH of a weak acid, weak base solution. So these acids and bases follow Ka and Kb values, which stand for acids and base, but these are just K values because you can think of it as just products over reactants. To get these K values. So we'll look at this a little later, so we're just going to go ahead and talk more about strong acids, strong bases. All right, so let's calculate the pH and pOH of these different solutions, right? All of these are going to be strong acid, strong base solutions, so recognize what assumption that you're making. So if we have a solution that is 0.025 molarity HCl, what is the pH? So what are we going to assume? That the given HCl concentration, because this is a strong acid, is equal to the H plus concentration. And remember, it's this value, H plus concentration, is what we need to calculate the pH of this solution. So we're assuming all of that HCl fully ionizes. That's our H plus, so we can simply do negative log 0.0250 molarity, and so we get that the pH is equal to 1.6. How many decimal places should I have? 3. So 1.602. pH, right? Because there's 3 sig figs, so 3 decimal places, right? So we added acid to a solution. The solution is acidic. It's much, much, much lower than 7. Okay, and again, we're assuming all of this is at 25 degrees Celsius. Okay, so what is the pH of a 0.175 sodium hydroxide solution? So again, this is a strong base, so we're going to assume that this completely ionizes. So we're assuming that the sodium hydroxide concentration is also equal to the hydroxide concentration. So simply, when I take the negative log of this number, what am I calculating? pH or POH? POH, because this is hydroxide concentration. So POH equals negative log 0.0175. And so this also has 3 decimal places. This is going to have 12.243. Oh wait, no, it's not. That's the answer. If you put this into your calculator, you get 1.757, all right? But is that the pH? No, it's the POH. Also, you might recognize that looks like an acidic regime because it's under 7. So recognize, oh no, I calculated POH. In order to calculate pH, I need to subtract that number from 14. So 14 minus 1.757 equals, now I have my 12.243. That is a more appropriate pH, right? It makes sense because we add base to a solution, so the pH should turn basic, yes. Okay, and then finally, what is the pH of a 0.003 molarity calcium hydroxide solution? So should I just plug that into negative log to get POH? What's the difference here? What's the difference in this one? What is our hydroxide concentration in this solution? Is it 0.003? No, it is actually 0.006. There's double the amount of hydroxide present because each calcium hydroxide donates 2 hydroxides. All right, so we double the amount of hydroxide. So then you just POH that value, you get something like 2.22 is your POH, and so then your pH is something like 11.78. 2 decimal places because that concentration has 2 sig figs. All right, and yes, that is a basic pH, so you can be satisfied that your pH value is correct because it matches your intuition. All right, so these are using pH, POH calculations, but using actual substances. In these examples, they're all strong acids, strong bases, so we can make a small assumption to assume what the H plus or OH minus concentration is in those solutions. All right, so let's do another one. So you throw a large scoop of barium hydroxide into water, it's not all the solid dissolves. So this means that this is a saturated solution. Right, we have solid sunk at the bottom, and there's some amount of concentration of barium hydroxide floating around in dissolved in solution. So if I tell you that the solubility of barium hydroxide is 0.1077 moles barium hydroxide per liter at 25 degrees Celsius, calculate the hydroxide concentration and the pH of this solution. All right, so I'm telling you that the solubility of this solid barium hydroxide is 0.1077 moles per liter or 0.1077 molarity, because that's what molarity means. It's moles per liter. All right? So, you know, if you look at this saturated solution, we have solid sunk at the bottom, but all this solution around that solid has a concentration of 0.1077 molarity. All right, so if that's the concentration of barium hydroxide in the solution, what is the concentration of just hydroxide? It's just double that. So hydroxide concentration is what is double that? 2154 molarity hydroxide. And so then to get our pH, we want to take the negative log of that OH minus concentration. So POH for this example is, something real small, 0.6668. So 4 sig figs 4 decimal places. And so to get our pH, it is 14 minus that small number we got. So our pH is 13 point, it's right there, 3332. So yes, in fact, this solution is quite basic because there's a lot of barium hydroxide dissolved, all right? And so barium hydroxide is another example where each formula unit gives up 2 hydroxides to aid to pH calculations. All right, so what if we take 1 liter of that saturated solution and then add 50 milliliters of water? What is the final pH of that diluted solution? So I have a nifty little picture for you here. All right, so we just calculated the pH of this saturated solution. We just calculated that this had a pH of 13 point whatever pH. Let's take 1 liter of this, all right, stick it into the bottom, 1 liter of that barium hydroxide solution, and then dilute it with 500 milliliters of water. Right? So this is just dilution. If we dilute the barium hydroxide solution, are we going to change the amount of hydroxide present? Yes. If we change the amount of hydroxide, will we change the pH of this solution? Yes, we will. So in order to approach this question, we need to take the molarities, apply dilution, and then recalculate our pH. So let's simplify this and determine how the dilution will occur. All right, so I take 1 liter of the saturated solution, I mix it with half a liter of water. So what is my total volume? What's everything in this new beaker? It has a total volume of 1.5. How many zeros? Probably 3. Okay, 1.5 liters of solution. So this V total, this is my V2 in my calculation. What is V1? It's the volume of the thing I'm diluting, so V1 is actually 1 liter, V1. It's the 1 liter of the saturated solution that I'm pulling out of the thing that I'm diluting, right? So V1 is equal to 1 liter, and it has an initial concentration of 0.2154 molarity hydroxide. We already calculated that before in the previous question, given the concentrations of everything. So I have V1, M1, and V2, so hopefully you see that we are going to calculate M2. What is the new diluted molarity of hydroxide? So M2 is equal to M1 V1 over V2. So M1 we just got is 0.2154 molarity of hydroxide times V1 is 1 liter over the new volume is 1.5 liters. All right, so we're not quite having the concentration. But we see that M2, the new concentration of hydroxide, is slightly diluted at 0.1436 molarity hydroxide concentration. All right. I don't know why I squared that. That's not our answer. Okay, that would be the answer if this was a Chem 1210. All right, like what is the new concentration? But now we're just applying the idea of, okay, we can report the concentration after dilution, but now we can also report the pH after solution because we have those pH equations. So if I negative log this number, what P am I calculating? POH, yes. So if you negative log that, POH equals, what is it? 0.8428, and so subtract from 14 because this is 25 degrees. We're allowed to do that. We get the pH that's given there, 13.1572. That is our answer. So it looks like when we dilute a basic solution, the solution becomes less basic. It goes from a higher pH, more basic, to less basic. Basically, we're diluting it closer to neutral. And so that hopefully should make sense. If we add more water, we're not neutralizing it, we're just bringing it closer to a pH of 7. But we only added a little bit of water, so it didn't change it that drastically. All right, so there's another pH calculation. All right, let's do another one. Yes, one more, 2 more. Okay. Let's calculate the pH of a mixture formed by mixing two different things together, some HCl and some HI. So these two substances are what? Acids, bases. They're both acids. They're both what kind of acids? Strong acids, all right? Both of them are strong acids. So I like to think of it as this. You know, to calculate pH, I need to figure out how much H plus do I have present in my solution. There's two sources of acid here. So I need to just calculate what is the total amount, what is the total concentration of acid I have present. But I have two sources. Some of my H plus is coming from HCl. The other is coming from HI, another strong acid, and it has a total volume. So what's the total volume? 175 milliliters, all right? So I need to figure out what's the total amount of H plus present in this solution to figure out, once I mix these things together, to figure out the total H plus to get pH. So here is a tip for the next two chapters. Okay, you might feel reluctant to use this tip now, but I promise you when we get to chapter 17, you're probably going to use it. All right, when we see how we have volumes and molarities, right? So when we multiply, so the unit of molarity is moles per liter, right? So you might think, oh, I need to convert both of these to a liter amount, right, to get a mole amount for this equation, but we don't really have to. So here's the trick, because we're in 1220 now, and I now can teach you the tricks to dimensional analysis, is most of the time we're working with really small volumes of things, so we can oftentimes just leave things in milliliters, all right? So if we're multiplying by a milliliter and then dividing by a milliliter later, it's not a big deal. All of those milliliters will cancel out. So my trick here for you is to keep things in milliliters and calculate millimoles of substance present, because when you divide a millimole by a milliliter, you get molarity out, all right? So here's the tip. A milliliter times a molarity gives you a millimole amount of substance. Then if you take a millimole and divide it by a milliliter amount of total volume, you get molarity out. So this saves you the step of dividing and multiplying by 1,000 all the time to convert milliliters to liters, which is oftentimes, we just undo it by the end anyway. So this question gets simplified because all we need to do is multiply these two numbers together. All right, if I take 50 milliliters times 0.02 molarity, I get that there is 1 millimole of HCl present. Versus saying, oh, converting it to, from milliliters to liters, 0.001 moles of HCl. I don't know which number you like to look out better, 1 or 0.0001. Yeah, 1 is nicer, okay? Then if we multiply these two numbers together, 125 times 0.01 molarity, if you just multiply them straight, you get a millimole, which is a number that's nice to look at. There is 1.25 millimoles of HI present. Versus if you converted it to liters, it would be 0.00125 millimoles. And that's annoying to look at because those are small numbers, right? And so with these whole numbers, it's very clear to see, oh, I have 1 millimole of this, 1.25 millimoles of that acid. What's the total amount of acid that I have in my container? 2.25, yeah. 2.25. So we get that the total H plus concentration in this solution, instead of doing mole amounts, we can say, oh, the millimole amount of HCl plus the millimole amount of HI over the volume in milliliters will also give us molarity in the regular unit. So we see, okay, 1 millimole of HCl plus 1.25 millimoles of HI over 175 milliliters. So see how I never converted to liters. As long as you keep everything in milliliters and calculate millimole amount of substances, then you're fine, all right? as long as we keep everything in milliliters. So we get, since both of these are strong acids, the molarity of HCl and HI is also the concentration of H+. We get that the concentration of H+ in this strong acid solution is something like 0.0128 molarity H+. And so when you pH or negative log that, you get your pH of 1.89. 2 decimal places, yeah, that sounds right, because these molarities only have 2 sig figs, right? All right. Okay, so that's my introduction to using millimoles. We'll use it more later, I promise, and it'll be useful, because dividing and multiplying by 1,000 all the time gets annoying, right? All right, so those are millimoles. All right, let's do one more. One more? Okay. Okay. So a solution possesses a potassium hydroxide concentration of that. At 50 degrees Celsius, what is the H+ concentration in this same solution? All right. So you might look at that KOH concentration. This is a what kind of substance? Acid or base? Base. What kind of base? Strong base. So if KOH is equal to 0.01 molarity, that means hydroxide concentration is equal to also 0.01 molarity. All right? So if we negative log that number, what value are we calculating? POH, yeah. So if you put that in your calculator, you'll get really used to pH calculations. I see that this decimal place has to move over 2 times, so I can tell right away that the POH for this is 2, because you have to move it over 2 times, because that's what the number out front means. It's how many times you move the decimal place over, right? I know that's not what the question asked for, but I just wanted to calculate it anyway, okay? Because if you missed the portion of this question that says, what temperature are we at? 50 degrees Celsius. What do you want to say? You want to say that the pH is 12, right? You want to. But that only works when? 14 equals pH plus POH only works when? At 25 degrees Celsius. So this saying, oh, pH equals 12 here, we cannot say this because we are not at 25 degrees Celsius, okay? All right, and that's the common mistake here. So instead, what we're going to do is use that given KW value that's given. So remember what KW is. It's the equilibrium for the self-ionization of water. So KW equals H+ concentration times hydroxide concentration at equilibrium. But in this case, instead of equaling 1 times 10 to the negative 14, it's equal to 5.5 times 10 to the negative 14. All right? So we want to calculate H+ concentration. Do we have the hydroxide concentration at equilibrium? Yes, we do. It was given in the question because this is a strong acid, or sorry, strong base. So we're just calculating here the H+ concentration using KW and the hydroxide concentration that's given. So 0.01 molarity hydroxide. And so then you get that this answer, the H+ present, is 5.5 times 10 to the negative 12 molarity H+. All right? So we cannot say that this is a pH of 12. It is not exactly 1.0 times 10 to the negative 12 H+ concentration. So our answer is D. And for fun, if we take the pH of the negative log of this number, we do get a pH of 12, or no, not 12, 11.26 instead, right? Because we are at a different temperature that has a different KW value. A KW of 1 times 10 to the negative 14, only at 25 degrees Celsius. That's only when pH plus POH equals 14. That's the only time that works. So at 50 degrees, we have to use this other KW value, but just recognize that that KW value represents this equilibrium expression. So we're given one, just calculate the other using this KW value. All right, so yeah. A, this solution is basic, so there's no H+, That's never true. Okay, water always self-ionizes with itself. Yes, I know that this is a basic solution, but there's always a tiny, tiny bit of H plus present, and you see that given the Kw, the self-ionization constant. And you do see here that the H plus concentration is much, much less than the hydroxide concentration, which is consistent with a basic solution, right? Okay, so there we go. There are our pH calculations using strong acids, strong bases. So do recognize what kind you're working with questions concerning those pHs of strong acids, strong bases. Okay, so question. Most of these pHs we've dealt with in the previous questions have been within the 0 to 14 realm of things. So the question is, can we have a negative pH? So let's try this. If we have concentrated HCl straight from the bottle, it has a molarity of 12.1 molarity, really strong. This stuff straight from the bottle. Calculate the pH of this. So if we want to calculate pH, we need H plus concentration. So what is the H plus concentration in this solution? 12.1. We can say that because HCl is a strong acid, yes. And these are the questions you want to be asking yourself, because are they always going to be strong acids? No, they won't. They're going to be weak acids here soon. So that means if we just negative log this number, negative log of 12.1 is actually negative 1.083. So yes, we can have negative pHs. Negative pHs are common for really, really concentrated acid solutions. If we have a really, really, really concentrated base solution, we can have pHs above 14 as well. All right. Again, you just plug it into the negative log expression to get that pH value. But for the most part, since we're calculating mostly dilute solutions, negative pHs aren't super common. Rarely will you get a calculated value with a negative pH in this class. We work with, really concentrated acids and bases, but once they're this concentrated, instead of expressing them as a pH, it's easier for us to express it as a concentration instead. So not going to be super common for this class, but you do work with this pH stuff in lab when you work with concentrated stuff. All right, so that's a negative pH. Okay. Anything with a molarity over 1 molarity will actually have a negative pH if it's a strong acid, FYI. Okay, and that's just the rules with logarithms. Okay, so there we go. All right, so those are strong acid, strong base calculations. So let's move on to the ways to categorize acids and bases. All right, so there's 3 different ways. We need to think about it. Okay, so no longer is it just, H plus OH minus making water. That's a generic neutralization reaction, right? So we're going to go back to like the beginning of the chapter where I'll define what acids and bases are. So these are 3 ways we're going to think about acids and bases in water, and this is really important in organic chemistry. Really important. If there's anything you take away and save for next semester when you take organic, it's these ideas. So I'm going to try my best. Okay, so these are the ways to categorize acids and bases. The first one is Arrhenius acids and bases. This is just thinking of the presence of H plus and OH minus. This is what we've been doing up until now. Where you look at the formula, you see H plus, that's an acid. You look at a formula, you see an OH minus, ooh, that's a base. We've been doing that up until now, but we're actually going to expand our definitions of acids and bases by looking at movement of either H plus hydronium in a chemical formula or the movement of electrons. All right, and those are the next 2 acid-base categorizations. We are actually going to focus on these last 2, Bronsted-Lowry acids and bases and Lewis acids and bases. Okay, so Arrhenius acids and bases. This is what we've known up until now. H plus, acid. OH minus, base. And this was the first acid-base theory to come out, where they categorized substances that were acids and bases, whether H plus or OH minus was present. But here's the thing, back then, way back then, did they know like the chemical formulas of stuff? If they were holding something, did they know it was like HCl? Did they know it was sodium hydroxide? They didn't, right? Because they can't see atoms, they can't see what elements make it up because they didn't have the instrumentation. So what Arrhenius did was reacted unknown substances, and if he saw certain observations, he classified it as an acid. If he saw a different set of observations, he classified it as a base, all right? So Arrhenius acids produce H+ in water. Arrhenius bases produce hydroxide in water. And so that fits with our definition we talked about earlier, all right? And so here were the observations he made. If a mystery substance was mixed with zinc metal, he saw gases, H2 gas being produced. This is actually the activity series, all right? Activity series back from Chem 1210. All right, so the activity series says that H+, when you mix it with H+ with zinc metal, produces a redox reaction. So if your mystery substance has H+ in it, he would observe gas bubbles being produced. So that's how he identified these substances as acids, if it produced bubbles, if it was mixed with zinc metal. Versus if you had a mystery substance and there was base, hydroxide present, if he mixed it with magnesium 2+, he saw a solid form. And that's because magnesium hydroxide is a solid. It's insoluble in water. And so the presence of that hydroxide he would be able to observe that presence when adding magnesium to it. Right? So if he mixed in a substance and it yielded no observation, it didn't make bubbles, it didn't make solid, then he was able to identify that substance, as a neutral substance, that it isn't acidic, it's not basic, it's neither. Right? So yeah, the idea of Arrhenius acid, Arrhenius base is just whether that substance produces H+ or hydroxide in that formula. And I'll note here, this is ammonia, this is our one weak base that we talked about earlier. How ammonia makes hydroxide in water is ammonia has a lone pair on it, grabs one of the hydrogens from water to leave hydroxide left over. And that's how ammonia, because technically it's hard to tell that this is a base because there's no hydroxide present, but that's only true for strong bases. So ammonia here is a base because it takes an H+ from water to make hydroxide in that solution. And that's an idea we'll talk about constantly in this chapter. Okay, so Bronsted-Lowry acids and bases still categorizes acids, bases the same. Like ammonia is still going to be a base. HCl is still going to be an acid. But we think about it differently, all right? We want to think about the idea of acids and bases and protons, or H+ moving in a chemical reaction, all right? So H+, like we know HCl is an acid. It contains H+. That H+ makes it acidic. We call that H+ a proton as well, because H+ literally just has a proton on it. That's it, all right? So when looking at an acid-base neutralization reaction, if we can locate how are the protons moving in this reaction, HCl donates its proton to neutralize something else, we can tell what is our Bronsted-Lowry acid, what is our Bronsted-Lowry base. All right? So a Bronsted-Lowry acid is a substance that can donate a proton, right? Donates protons. I always think of HCl. That's like my prototypical acid. HCl can give up its H+ and give it to something else. That is why it's an acid, because it can give up that H+. Versus a Bronsted-Lowry base is a proton acceptor. It takes protons from acids. So if you think about like hydroxide, which is like a strong base, hydroxide gets neutralized when it takes an H+ from something else because it becomes water, right? So hydroxide, which is a base, is a proton acceptor because that's how it gets neutralized, right? And so in order to identify bronzidyluric acids and bases, we need to understand the structure more. And so this didn't come later with history because back when Arrhenius did all of his observations, they didn't understand structures, but now we do. And so we'll pick up here on Thursday, talk more about acids and bases, the structure, and how to categorize them.